So this is 3.4, and we're going to be discussing concavity, the second derivative test, and we're going to learn what points of inflection are. So this second derivative test is tomorrow, so we won't be discussing that much today, but we will need to use the second derivative. So concavity is the curvature of a graph, and it can be described in terms. It basically means it's concave up or concave down. Think of an umbrella. So you've got your umbrella, that's concave down, and a smile is concave up. So here's two pictures. You might want to take a minute and write them down. So we've got concave up, your smile, and concave down, your frown. Most graphs do both, especially when we're looking at polynomial graphs. Some graphs don't. It's just a matter of what's going on with them. So this is our two types. Here is our favorite graph we've been discussing quite a bit lately. We can see it's how it has two. Here's my concave up portion. Here's my concave down portion. What we're going to do today is figure out how to find these parts. So we're using these words concave up and concave down. So concavity is focusing from the second derivative instead of the first. If you've been recalling, we've been talking about max and mins, which is the first derivative. Concavity is the second derivative. So we're going to pay attention to the sign of the second derivative. When is it positive and when is it negative? So first we've got to find it. Let's go ahead and take the derivative of this. We're going to change it really quickly into 3x squared minus x cubed, because that's easier to take the derivative of. F prime, our first derivative, is 6x minus 3x squared. And our second derivative is 6 minus 6x. Okay, so there's our second derivative, and let's set it equal to 0 to figure out when it changes from positive to negative. So that's going to be negative 6 equals negative 6x. So x equals 1. So at x equals 1, it's going to cross the y-axis. So just on this graph, what I have here, let's go ahead and graph our second derivative. So f double prime of x was 6 minus 6x. So the y-intercept is 6. The slope is 6. And the x-intercept was 0. That's what I just found out by setting it equal to 0. With a slope of 6, so it does something like that. That is a very bad graph, but it's good enough. It gives me the idea. So I've got my derivative. I know it's 0 here, and that's what's happening. Notice what's happening right here at the value where it's equal to 0. See this point right here, how it's changing from being concave up, to concave down. It's changing right there. That point that we just found has a special name. So, but notice that the second derivative, the sign, which is what I said to pay attention to, over here the sign is negative, and over here the sign is positive. And so that's what's happening there, is those kinds of switches from positive to negative. It's pretty straightforward, not too complicated. Depends on how complicated your second derivative is. So remember I said this point had a special name. It's called the point of inflection. And the point of inflection, by definition, is where the graph, where the function, let's call it f of x, changes concavity. So we know with max and mins we have things called critical values, and that's where we know that, so like this, our critical values are where the first derivative equals 0. The points of inflection are where the second derivative equals 0. So that's what we found there. And so that's our definition for point of inflection, Okay. Feel free, by the way, if I'm going too fast, pause the video, slow me down. That's the only way you're going to do it, because I'm going to just keep going ahead. So what we have just discovered is when f prime, double prime of x is greater than 0, then the original function is concave up. When f double prime is less than 0, then the original function is concave down. Or in other words, positive or negative concave down. here's an important idea. When a graph is continuous and switches from concave up to concave down or vice versa, we call that a point of inflection. So there's another definition of point of inflection. And again, pause the video so you can write this down because I'm going to keep going. So how, and this is a little low, how does the first derivative relate to concavity? So in this picture, I have the graph of the first derivative. And how is it related to concavity? So we know the point of inflection is when x is 1. And what's happening to the first derivative there? So we're going to stare at this picture for a little while and come up with a conjecture. Go ahead and pause the video and think about it for a minute. And we're thinking about how this question, how is the first derivative related to concavity? What happens to the first derivative? Is there a relationship? Again, you're pausing, you're making a guess. What do you think? So here is the relationship. It's related to the first derivative, specifically the increasing and decreasing aspect of the derivative. If f prime of x is increasing, then f of x then is concave up. If f prime is decreasing, then f is concave down. So look at that. When it's increasing, the function is concave up. When it's decreasing, the function is concave down. So that's the same kind of relationship we have, and so we have these three things we do. So all three of my derivatives on the same picture. So we've got our original function in blue, our first derivative here in red, and our second derivative in darker red or maroon. Our point of inflection, which is related by this dotted line, we have right there. And so we can see that using the first derivative test of these two relationships, that when this changes, that's our maximum, how it's changing from negative, from a positive, from increasing to decreasing, so we have a max. And that's the same where the point of inflection changes for this concavity. So there's a lot going on there. And again, I'm talking way too fast. So take a minute, do what you can to kind of convince yourself of what's going on here and the relationship between these three. We will spend more time talking about this. So you're going to want to pause the video now to write all of this down. So I'm just going to read it to you. So you're going to want to pause it so that you can get a chance to write it down. So finding points of inflection. Step 1, find the zeros and the undefined values of the second derivative. So just like with critical values, we have to find both the zeros and where the second derivative does not exist or is undefined. We call these points PPOIs. And I don't remember what that stands for. I'll look that up. Use the PPOIS's to determine possible intervals. Possible points of inflection. Sorry, I remembered. So possible points of inflection to determine the possible intervals. Find the sign of the second derivative in each of the intervals from step 2 and determine whether each interval is concave up or concave down from step 3. So let's try it. So the first thing we're going to do is take the derivative of my new function. Then I'm going to take the second derivative. I'm going to set my second derivative equal to 0. I'm going to solve that. I'm going to factor out 12x, and I leave behind x minus 2 equals 0. So my possible, so x is 0 or 2. Okay. So we're going to continue. We're going to do very much similarly to as we were doing points of, as we were doing critical values for our possible points of inflection. We're going to create, we're going to create a number line test. So we've got our possible points of inflection at 0 and negative and positive 2. We're going to check numbers. So we're going to check 1, 3, and negative 1 and see what the signs are. We're checking in the first derivative, the second derivative, excuse me. So when I plug in 1, I'm going to get 12 minus 24, so that's a negative number. When I plug in negative 1, I'm going to get 12 plus 24, so that's a positive number. When I plug in 3, I'm going to get 9 times 12 minus 9 times 12, which is 108, minus 24 times 3, which is 72. That is a positive number. So that means since it's positive to negative and negative to positive, I'm trying to do now, I've got my signs of my intervals, concave up or concave down. This one is concave up, concave down, concave up. So up, down, up. That's what my second derivative tells me. So that's what I'm trying to figure out. I'm going to leave you to your luck. You're going to want to try a few more problems, look at what's on WebAssign, and we will talk about this again on Friday because tomorrow you have a quiz. Good luck.